In the previous lecture, we have studied about RPC and we saw how RPC works. And I also told you that during the working of an RPC, there are certain issues that we face and we have to address those issues. So in this lecture, we'll be studying about the issues that we face during the execution of an RPC, and we will also see how they are resolved. So first let us see what are the issues, and then we will see how each of them are resolved one by one. So the first issue that we face is difference in data representation on the client and server machines. So this is the issue where the data representation is different on the client and the server machines. Like for example, for the representation of 32-bit integers, some systems known as the Big Indian use the high memory address to store the most significant byte, while other systems known as Little Indian store the least significant byte at the high memory address. So though both systems are having a 32-bit integer pattern, but the way they represent it is different. In the Big Indian systems, the high memory address stored the most significant byte, while in Little Indian system, the least significant byte is stored at the high memory addresses. So the way the data is represented becomes different. So in case of local communications in inter-process communications, this kind of problem does not arise because we are having communication between processes residing in the same machine or the same system, and this kind of problem will not be there. But in case of RPC, we are dealing with communication between systems located at different places connected via a network. So these systems may be having different kind of data representation. So if you are sending something from a system that represents data in one way to another system that represents data in another way, then there will certainly be an error. So this is one issue that we face in RPC. Now let us see how this issue is resolved. So in order to resolve this issue, RPC system defines a machine independent representation of data. One such representation is known as the external data representation, or XDR. On the client side, parameter marshalling involves converting the machine-dependent data into XDR before they are sent to the server. On the server side, the XDR data are unmarshaled and converted to the machine-dependent representation for the server. So this is how the issue of difference in data representation is solved in an RPC. So RPC system, they define a machine-independent representation of data. So what that means is, whatever kind of data may be generated by a system, it is converted into a machine-independent representation. So it is converted in such a way that the data does not depend on the machine anymore, but it can be used in any kind of machines. So one such representation is known as the external data representation, or XDR. So when the data is converted to an XDR, then that becomes a machine independent representation. And on the client side, parameter marshalling, we have studied about parameter marshalling in the previous lecture. So parameter marshalling involves converting the machine dependent data into XDR before they are sent to the server. So on the client side, the data will first be converted to XDR form, and then on the server side, what happens? The XDR data are unmarshaled and converted to machine dependent representation for the server. So the data from the client is converted into an XDR format before they are sent to the server. And when the server receives that, on the server side, it is unmarshaled and converted back from the machine independent form to the machine dependent form, and it is given to the server. So that is how the issue of difference in data representation on the client and server machines are solved in an RPC. So now let us come to the next issue. So the next issue is that whereas local procedure calls fail only under extreme circumstances, RPCs can fail or be duplicated and executed more than once as a result of common network errors. So again, in case of local procedure calls, this kind of issue does not arise much, because a local procedure call will fail only under extreme circumstances because the call is happening between the same machine. But in case of RPC, there is a great chance of failure, and there is a chance of duplication of the procedure calls, and also there is a chance of the procedure calls being executed more than once. And why does this all happen? Because RPC works between systems connected via a network. And when things are happening via a network, there are many problems that can arise due to network errors. They are prone to network errors. So for this kind of issue, let us see what is the solution that we have or how can this be resolved. So the resolution for this is the operating system must ensure that messages are acted on exactly once rather than at most once. Most local procedure calls have the exactly once functionality, but it is more difficult to implement. So when this kind of problems occur due to network errors, we said that the calls could fail, they could be duplicated or executed more than once. So in order to solve this, what we are doing is we are going to make the operating system ensure that the messages are acted on exactly once rather than at most once. So let me explain what is the meaning of exactly once and at most once. So in case of at most once, whenever the client is sending something to the server, so let's say it is a procedure call. When the client is making a procedure call to the server will receive the call. So in normal circumstances, if we assume that no errors occur, then the server gets the call and it executes the call. But from the client side, it keeps on sending the messages again and again, and the server checks if this message was already addressed or if this message was already executed, and if it finds that it is already executed, then that message is ignored. So that is one way it can work. But as you see, this is not a very efficient way, and also there can be a chance where the procedure call never gets executed, because from the term at most once, what we mean is it should be 1 or it can be even less than 1. That means it can also be 0. So a particular call may never be executed if we follow this at most once functionality. So instead of that, what we have is we have an exactly once functionality. So in exactly once, we make sure that the procedure call gets executed exactly once, not more than 1, not less than 1, but exactly once. So in order to implement this, we have a system of acknowledgement. So we have to follow the system of acknowledgement where the client sends the request to the server and the server has to process the request, and after it has processed it, the server must send an acknowledgement back to the client saying that the request have been fulfilled. So once the client receives acknowledgement, it understood that the service was executed and it does not send the request again. But if the client does not get the acknowledgement, it keeps on sending the request again and again to the server until and unless it gets the acknowledgement. So when the server makes sure that it finished the execution, it will send an acknowledgement, and when the client gets the acknowledgement, the client understands that the process has been completed and it does not send the same request again. So in this way, we make sure that the messages are acted on exactly once. So this is a much better and efficient way to tackle this problem. So even though RPCs can fail due to network errors, by following these methods, we make sure that the requests are executed exactly once. And if they are not executed, the client can keep sending it again and again until it is executed. So that is how this problem is solved. Now let us see what is the next issue that we face. So the next issue is, with standard procedure calls, some form of binding takes place during link, load, or execution time, so that the procedure's call's name is replaced by the memory address of the procedure call. The RPC scheme requires a similar binding of the client and the server port, but how does a client know the port numbers on the server? Neither system has full information about the other because they do not share memory. So in this issue, what we are talking about is, whenever a procedure call is made, though we are calling the procedure by its name, eventually the procedure has to be addressed by using its memory address. And also we know that every process is having a port number associated with it on both the client and the server. Though the client knows which procedure to call by its name, but it does not know the address or the port number of that particular procedure. So how can it work when the client and the server does not know each other's port numbers for its different procedures? So neither system has full information about each other because they do not share memory. Since these two systems reside in different physical locations and are connected via a network, and since they do not share any memory, so both the client and the server do not have full information about each other. So how do we solve this issue? Let's see. So this issue can be solved in two different ways, and we will be seeing both of them. So the first way is the binding information may be predetermined in the form of a fixed port address. At compile time, an RPC call has a fixed port number associated with it. Once a program is compiled, the server cannot change the port number of the requested service. So in this first solution, what we have is we have a predetermined binding information in the form of fixed port addresses. That means the address of the ports will be fixed. They will not be changed. So at compile time, an RPC call has a fixed port number associated with it, and once the program is compiled, the server cannot change the port number. So once we have the fixed port number, we can know which procedure to call based on that port number, because the port number is fixed and we can get information about that during the compile time. But this, as you see, is not a very flexible way, because the port numbers have to be fixed. And if due to any reason we want to change the port number, we cannot do it because the port number has to be fixed in this kind of system. So we have a second solution which is better and more flexible and dynamic than this. So let's see what is that. So in the second solution, what we have is bindings can be done dynamically by a rendezvous mechanism. Typically, an operating system provides a rendezvous, also called a matchmaker daemon, on a fixed RPC port. A client then sends a message containing the name of the RPC to the rendezvous daemon, requesting the port address of the RPC it needs to execute. The port number is returned and the RPC calls can be sent to that port until the process terminates or the server crashes. So in the second solution, what we have is we can do the binding using a rendezvous mechanism. So what we mean by this is the operating system provides a rendezvous daemon on a fixed RPC port, and it is also known as a matchmaker. This matchmaker will help us, and let us see how it will help. So the client sends the message containing the name of the RPC to the rendezvous daemon, requesting the port address of the RPC it needs to execute. So what the client will do is, when it wants to request for a procedure call from the server, it will send the name of that procedure call to the matchmaker or to this rendezvous daemon, and it will ask the matchmaker to return the address of that procedure. And what the matchmaker will do, it will look up the name and it will find the address or the port number of that RPC and it will return it to the client. And then the client knows to which port it has to send the request. And so the request will be forwarded to that particular port containing the RPC. And the RPC calls can be sent to that port until the process terminates or the server crashes. So this, as we see, is a much better mechanism, because here we do not have to have a fixed port number, because the matchmaker will always take care of finding the port number of a particular procedure's name and it will return it to the client. So even if the port numbers or the addresses gets changed, it's okay, because that will be stored in the matchmaker and the matchmaker will help the client to find out the port number of a particular process based on its name. So this is how this problem is solved. So those were the issues that we face in an RPC, and we saw how these issues are resolved. Now let us see how does the entire execution of an RPC takes place. So in the previous lecture we have seen how RPC works, and now we have seen how RPC faces issues and how those issues are resolved. So as a whole, now we will see how does RPC work together by solving this issue, and we will try to understand the entire working of an RPC using a diagram. So here I have a diagram which shows the execution of a remote procedure call RPC. On the left side we have the client, and on the right side we have the server, and in between we have the messages which are sent either from the client to the server or from the server to the client. In the client side, the user calls the kernel to send RPC message to procedure X. So in the client side, the user needs the service of some procedure which we call X from the server. The server is some other system that is remotely located somewhere else. So the user wants to use that service, and the name of that service is procedure X. At this moment, we only know the name of the procedure and we do not know its address or the port number. So the user calls the kernel to send the RPC message to procedure X. So what the kernel will do is the kernel sends message to the matchmaker to find the port number. So we have just studied about matchmaker, and what does the matchmaker do? The matchmaker stores the information about the port name and their numbers, and it can look up those numbers and return it to the client that is requesting them. So the kernel will send the message to the matchmaker to find the port number. So this is the message that goes to the matchmaker. So this message is from the client, and it goes to the server side, to the server, and the port to which it is addressed is to the matchmaker's port. So we are sending a message from the client to the server to the matchmaker port on the server, and we are requesting for the address for RPC X. So we are requesting the address of procedure X. So what happens is, on the server side, the matchmaker receives this message and looks up for an answer. So the matchmaker will look up what is the address or the port number of procedure X. So once it looks up and once it finds it out, the matchmaker replies to the client with port P. So we are taking an example here of port P, which means that the procedure X is on port number P. So port P is the port to which we have to send the message in order to access procedure X. So the matchmaker found that out and it replies that to the client. So this is the message that goes from the matchmaker to the client side. From where does it go? From the server side. It is from the server side. And where is it going to? It is going to the client. And the port to which it is going is to the kernel port on the client side. And it replies, or it returns, the port number P. So here in the client side, the kernel got the port number of the procedure that we were interested in. So the kernel places port P in the user's RPC message. And let's see what happens further. Okay, so after the kernel places the port P in the user's RPC message, the kernel sends the RPC. So now we have got everything that we required. We got the port number of the procedure in which we were interested in, and then the kernel now sends the RPC to that port where procedure X is residing. It is sending a message from the client side to the server, and to which port? Port P. We found out that the procedure X is in port P. So we are sending it to port P and we are sending the contents of the RPC. So what are the contents? We studied that we may consider the procedure as a function or a service that is executing some task. So we need to pass the parameters for that. So those parameters and everything will be contained in this contents. And so this message is sent to the server side. The daemon listening to port P receives the message. So in the previous lecture, I also explained what are daemons. Daemons are softwares that are always listening for some incoming requests, and based on that they will act. So there is a daemon on port P which is listening for incoming messages, and it receives the message which was sent from the kernel. And after it receives, what happens? The daemon processes the request and sends the output. So that function or that procedure which was called will be executed with the parameters that were passed, and then after execution the output will be sent back to the client. So it will be again sent using a message, and here there is a message going from the RPC's port P. So this message comes from the port P of RPC because it is coming from procedure X, and port P belongs to procedure X. So it is from RPC port P and it is going to the client. And to which port on the client? To the kernel port on the client, and it sends the output. So the kernel on the client side receives the reply, which is the output, and it passes it to the user. So the user has got the output to the procedure that he has called. So that is how the execution of an entire RPC takes place. So with this, I hope the concept of RPC is clear to you, and I hope you understood how RPC works and how the issues are resolved and how the execution of an RPC takes place as a whole. So I hope this was clear to you. Thank you for watching and see you in the next one.